subgroup just as a review. Just as a review, today I will discuss normal subgroup. Just recall what is the definition of normal subgroup. We all of us know. In my previous video, I had discussed the normal subgroup briefly. There are many various type of video about normal subgroup. Today I will discuss normal subgroup just as a review. Just recall. If you don't see my previous video, at first see my previous video. The definition of normal subgroup is if A is a subgroup of the group G such that there are no distinction between the left coset and right coset. That means here GA is equal to HG. This is true for all every G in G. That means here GA is equal to HG. This is equal just as a set. That means the set GA is where H belongs to capital H equal to the set HG where H belongs to capital H. This does not imply GA is equal to HG for all H belongs to H, but only for all H belongs to H there exists H dash belongs to H such that GA is equal to H dash G or vice versa. That means the set equal, but it does not imply the element are all equal. As for example, in S3 permutation group S3, consider the subgroup A is equal to sigma, cyclic subgroup generated by sigma, where sigma equal to the cycle 1, 2, 3. And then A is equal to identity sigma and sigma square, which is equal to the set containing element identity 1, 2, 3 and 1, 3, 2. If we consider tau equal to 1, 2, then tau A is equal to tau sigma square. And this is equal to 1, 2, 2, 3 and 1, 3. And A is tau equal to tau sigma square tau. This is equal to 1, 2, 1, 3, 2, 3. Notice these two sets are equal, but notice here the element, here tau sigma equal to 2, 3 and sigma tau equal to 1, 3. These are different, both different. So, in set notation, there are no distinction between left coset and right coset when the subgroup is normal subgroup. I hope my all viewers have understood this is clearly. Okay, well. That means when A is be the subgroup, then for normal subgroup, these following are equivalent. GA is equal to HG and this is true for every G in G. Then this implies G A is G inverse equal to H and this is true for every G in G. That means A is invariant under the conjugation. Third, GA is G inverse contain H and this is true for every G in G. Therefore, that means actually the normal subgroup is the definition, another definition we can write such way: GBA group and a normal subgroup A is of the group G is a subgroup which satisfying the given condition G belongs to capital G and H belongs to capital H such that G H G inverse belongs to this H. That means this is actually from this left coset when there is no distinction between left coset and right coset, this implies this. So this is another definition of normal subgroup. This is actually same. This means actually the left coset and right coset both are equal. We all of us know this part. Actually just as a review, after a long day I have defined the normal subgroup just as a review. Now I will say some properties of normal subgroup. I will see some properties of normal subgroup. When actually G is abelian group, then every subgroup is normal. This is because Gi is G inverse. Since the group is abelian, so this implies this is equal to G inverse S, and G inverse means this is actually identity. So this is equal to S, small s, which belongs to capital S. That means when the group is abelian, then every subgroup is normal. I hope my all viewers have understood this is clearly. Second property, when now consider G equal to S3. In few minutes ago I had seen A3 is a normal subgroup in S3. But if we consider this subgroup A is equal to E12, then 1, 2, 3 with A, this equal to set containing the element 1, 2, 3, 1, 2, 3 with 1, 2. And this is equal to nothing but this is equal to 1, 2, 3, 1, 3. Similarly, A is with the permutation 1, 2, 3, this is equal to 1, 2, 3, 1, 2 with 1, 2, 3. And this is equal to actually 1, 2, 3 and 1, 2 with 1, 2, 3. This means 1 goes to 2, 2 goes to 1 and 3 goes to 3, and here 1, 2, 3 means 1 goes to 2, 2 goes to 3, 3 goes to 1. And by this composition, this value would be 2, 3. Notice, here left coset not equal to right coset. So, this subgroup not be normal subgroup in S3. I hope my all viewers have understood this is. That means when the subgroup is abelian, then always that imply all subgroup be normal. But when the subgroup are not abelian, then there may be exist some subgroup which is normal. Also there may not be exist some subgroup which is not normal. I hope my all viewers have understood this is clearly. Okay, well. Let's see some example. We all of us know this is of normal subgroup. If there exists a group homomorphism phi from G to G dash, then kernel always be normal subgroup. Because if we consider G belongs to capital G and H belongs to car phi, then G is G inverse. This is always belongs to car phi. Why? Because we all of us know this part. Phi G is G inverse by the property of group homomorphism. This is equal to phi G times phi H times phi G inverse. And since H belongs to car phi, that means phi H equal to EZ dashed. This is equal to EZ dashed. This is phi G and phi G inverse means phi G inverse. And by the property of homomorphism, this is equal to phi G G inverse. And this is equal to actually EZ. So, phi of EZ equal to EZ dashed. So, that implies GH G inverse belongs to car phi. So, car phi is a normal subgroup of the group G always. Since G inverse belongs to car phi, where G belongs to capital G and A belongs to car phi. This is actually the property of homomorphism. So car phi always be normal subgroup. So in group homomorphism, if you can to find the kernel of this group homomorphism, you will see this is actually the normal subgroup of the group G. This is one way to find the normal subgroup of a group. At first we have to find group homomorphism, then we have to find kernel, and this kernel is normal subgroup of the group G. Similarly, another way to find normal subgroup is ZG. We all of us know ZG means center of a group. ZG always be normal subgroup of the group G. ZG always normal subgroup because if we consider G, one element G belongs to capital G, means the group, and A belongs to ZG, we have to show G, A is G inverse. This belongs to this subgroup ZG. Then obviously ZG is a normal subgroup. This we have to show. And G is G inverse since ZG is a abelian group. So if G be the member of the group G, so ZG means those set which commute whole group, whole element of the group. So A is G inverse would be G inverse A, and G inverse means actually identity. This is equal to A, which belongs to ZC. That means G A G inverse belongs to ZG. So ZG is a normal subgroup. I hope my all viewers have understood this is clearly. Okay, well. So center is a normal subgroup, or also kernel is a normal subgroup. Actually today's part is as a review part. In my previous video this part I had defined briefly. Just as a review. Today I have defined this part again. Today I will stop here. In my next video I will discuss some more question about silo group. This is also just as a review. Okay. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.